Dependence is why we build joint models, and conditioning is how we use it. Observe something, update everything else. In this video, we condition a random variable on an event and watch a familiar ratio produce a genuine PMF. Then condition on another random variable, which turns out to be a slice of last video's table, renormalized, and put the machinery to work on a result that deserves to be famous. Thinning a Poisson stream leaves it Poisson. Chapter 4 defined the conditional probability of one event given another. Random variables inherit it directly. The conditional PMF of x given an event S weighs each value by the same ratio, the probability that x equals x and S happens over the probability of S. Is this still a PMF? Yes, and the reason is elegant. The events x equals x partition the sample space, so by the total probability theorem, their intersections with S add up to the probability of S itself. Divide and the conditional masses sum to exactly 1. Here is the picture to keep. A packet is retransmitted until it gets through, so the number of trials is geometric. But this system gives up after n failures. Given that the packet made it, what does the trial count look like? Only the first n bars survive. Their shape is untouched. Each one is divided by the same number, the probability of success 1 minus p to the n. Conditioning kept the geometry and rescaled the mass. The bars beyond n vanish, the rest grow just enough to carry mass 1. Now condition on information of a richer kind, the observed value of another random variable. Go back to the joint table. Observing x equals x means the experiment landed somewhere in one row, so keep that row and forget the rest. The row's masses don't sum to 1, but we know the fix divide by the row total, which is exactly the marginal of x at x. That is the whole definition. The conditional PMF of y given x equals x is the joint mass over the marginal mass, defined whenever the marginal is positive, because conditioning on something that cannot happen means nothing. And notice the plural. Every value of x carves its own row and its own conditional PMF. Conditioning on a random variable hands you a whole family of distributions indexed by what you might observe. Slide the observation, and the distribution of y responds. That responsiveness is dependence made visible. Two kinds of conditioning, then, on events and on random variables. They are the same idea in two dresses. Any event S has an indicator variable, 1 when S happens, 0 when it doesn't. Conditioning on S is precisely conditioning on that variable taking the value 1, and conditioning on x equals x is just conditioning on an event. Each view contains the other. One more gift before the payoff. Read the slice formula backwards. The joint mass equals the conditional times the marginal. That is the product rule, and it means joint distributions can be built the way experiments actually unfold. First draw, then second draw given the first. Now let the machinery earn its keep. A transmitter sends bits. Each is a 1 with probability p, a 0 otherwise, independently, and the number of bits sent in an interval is Poisson with parameter lambda. Question: what is the distribution of the number of 1s? Condition on the total. Given that k bits were sent, each independently a 1 with probability p, the count of 1s is binomial with parameters k and p. That much we have known since Chapter 5. Now uncondition with the product rule. The mass of m1s sums the binomial times the Poisson over all totals k. Shift the index and the sum telescopes into the series for an exponential. What remains is unmistakable. Lambda p to the m over m factorial times e to the minus lambda p. The number of 1s is Poisson with parameter p times lambda. Thin a Poisson stream at random, and it stays Poisson, just slower. The key idea of this video: conditioning is slicing the joint and renormalizing, and run backwards. It builds joint models one stage at a time.